All right, so we're back with some more specialist maths. This is the differentiation section. So the first part, we'll just talk about what differentiation is, sort of big picture stuff. And then we'll look at some specific functions that are really useful for the course. So some prior knowledge for this that would be very helpful is to have a strong understanding of limits and first principles. I'll put some links below if that's unfamiliar to you, but I assume you might be doing the methods course as well, and you talk about that a fair bit there. Basic derivative rules. So, the power rule, if you've got some function x to the n, then the derivative is nx to the n minus 1. And just some understanding of function types. Obviously our trig functions, sine, cos, and tan, e to the x and log e of x, understanding those, their domains, their ranges, that sort of stuff will be very important. And as it says there, the domain and range of a whole range of different functions. So the concepts we'll cover in this is what is differentiation, sort of the big picture. Then we'll look at the product rule, the quotient rule, Leibniz and function notation, so two different ways we can sort of notate calculus. Then we'll look at the chain rule, and then we'll look at the derivatives of tan x and log e of mod x. All of these things I've covered in more detail elsewhere, like the product rule and the quotient rule. I've done proofs of those, but this is sort of just to remind you of the big key concepts of differentiation for spec maths. So let's jump into it. If we look at differentiation as sort of big picture, it's basically saying if we have some point A, that's at the point A f of A. So this blue function is the function f of x. And if we have some point on that function that's at the point A, then the y value at that point is just f of A. And then what we're saying is the gradient of the graph at that point is f dash of A. So what we've got here is just this blue function f of x. We've got this point A. Then I've drawn a tangent line L in this pink line. So you can see that that's a tangent to f of x at the point A. But what we can do is we can actually find the derivative and sort of understand what's going on here. So we'll say that these A values line up, and then this f dash of A value is basically how steep this pink line is. What's the gradient of it if you think of linear relations? So if I start moving it, we can see that it's going to trace out different values. So you can see at the moment, the gradient is getting smaller. It's getting sort of shallower, if you like to think about it like that. And then it's going to get to the top here where the line's actually going to be horizontal. So it's going to be horizontal there. And so you can see that the gradient goes to 0. F dash of A is 0 at that point. And then the gradient becomes negative. It becomes negative in between here. Negative, 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 and then it becomes 0 again when it's horizontal, and then becomes positive. So we can see that the gradient function also sketches itself out in this sort of fashion. And in this case, the blue line happens to be cubic, and the green line, which is the derivative, or the gradient function, is a quadratic. It has the power of 2 as its highest power. Okay, so, and you can do that with every function, right? That is what the derivative is. It's the slope of a tangent line at every point. And the other thing I'll just point out is you'll probably notice this angle here. So this angle here is theta, and this is the angle that this line L makes with the positive direction of the x-axis. So we say that if the line L is a tangent to the graph, as we have here at the point A f of A, and L makes an angle of theta with the positive direction of the x-axis, then the gradient of L is equal to tan theta. And you can think about it like this. If you were to make a triangle here, tan is the ratio of the opposite side to the adjacent side. Well, that would be rise over run. So you can see why tan of this angle would be equal to the gradient of the function at the point A. Because, tan is the ratio of opposite to adjacent, which is rise over run, which would tell you the gradient of this pink line. And my graph, I couldn't fix this, but see how over here it becomes a bit wacky. The positive direction of the x-axis wouldn't be this angle all the way around. It would just be from here all the way around, just around to here. Okay, it's just that I couldn't fix that. I can't make it appear as always the positive direction of the x-axis, whereas this part here is fine. Sometimes it just gets a bit wacky, like in between there. It's showing the angle all the way around. Okay, so hopefully that makes a bit of sense. That's sort of the big picture of differentiation. If we look at the product rule now, so the product rule is a way that we can differentiate functions that are products of one another. So if you have a function f of x and it's a combination of g of x multiplied by h of x, product means multiplication, then we say that the derivative f dash of x is equal to the derivative of g multiplied by the original h of x plus the original g of x multiplied by the derivative of h of x. And this notation here is function notation for calculus. And so if we look at an example, imagine f of x is x squared multiplied by sine x. You can see that that's a product of two functions. Then f dash of x, all right, well, we'll just follow this rule, is the derivative of g of x. So the derivative of x squared is 2x. And then we leave h of x the same, so that's sine x. And then we leave g of x the same, but then differentiate sine, so we get cos x. So yeah, we can see that the derivative is 2x sine x plus x squared cos x, and that's actually what we have in green here. This is the original function in green. I think it looks pretty cool. Has some interesting behavior around x equals 0, as you might expect. And this is the same thing, but just in a different notation. So this is Leibniz's notation. And yeah, it just uses it slightly differently. So it says if you've got a function y equals u multiplied by v, then dy dx is u times dv dx plus v times du dx. So same logic. U is x squared in this case. V is sine x. And so y equals u times v, and then dy dx. You follow the exact same process. You just use a different notation, and you'll get the same answer. And sure enough, that's what's in blue. So we can call it f dash of x, or we can call it dy dx, depending on which notation you prefer to use. And yeah, that's the blue function. So the blue function describes the gradient of the green function at every point x. So pretty cool, huh? All right, let's look at the quotient rule. So if we look at the quotient rule is when you have two functions divided by one another. So for example, you have g of x divided by h of x. Okay, and what it says is in order to find the derivative of f of x, you do this. You take g dash of x multiplied by h of x minus g of x times h dash of x divided by h of x squared. Okay, and here's just an example. I encourage you to get a pen and paper out to work it out fully so that you're confident doing it. But what you'll see is that if we have a function on the top, which is x squared plus 1, and in the denominator we've got h of x, which is x plus 3, and then the derivative, we're just following all this, is this business here. Okay, same logic down here. So pause the video, have a look, but just using a different notation. The top one is u, and the bottom one is v. Now, the quotient rule is a little bit more challenging in the sense that you have to get the order of things right, okay? If you look at the product rule, it didn't matter which order you did things because you're adding and you're multiplying, and they're commutative, so it doesn't matter which order you multiply and add, but it does matter which order you subtract. So it needs to go v du dx minus u dv dx divided by v squared. And sure enough, this is the graph. So in green, we have our function f of x, which is x squared plus 1 on x plus 3. Interestingly, it has an asymptote at x equals -3. I encourage you to think about why that's the case. And then if you take the derivative, you get this function, f dash of x, which is in blue. And it looks like this. So again, for the same reasons as before, the slope of a tangent line at every point on this green graph would trace out this blue graph. And so that's an example of the quotient rule with the different notations. All right. If we look at the chain rule, another interesting sort of graph here. A chain rule, I often find students find it a little bit confusing because it is a bit tricky. But if you've got some function f of x, and that's a composition of functions, so you've got some function h, I should say you've got some function g of x composed inside some function h of x. Then f dash of x, so the derivative of that function, is h dash of g of x multiplied by g dash of x. Basically, differentiate the function as if g of x was a single variable and then multiply by the derivative of the inside. Maybe an example will help. So if we look at f of x equals sine x squared, you can see that if we determine that x squared is an inner function, g of x, and the outer function is sine of x. You sort of got this sort of nested like Russian dolls here. So we can say that the derivative is, all right, the first part says take the derivative of sine as if x squared was just a single variable. So don't sort of change what's on the inside. So the derivative of sine is cos. So the first part would just be cos of x squared, and then you multiply by the derivative of the inside. So to be times 2x, because the derivative of x squared is 2x. I think this is where Leibniz notation comes into its own a little bit, because, I don't know, you sort of define it as the inner function as u. So if you've got some function, y equals h of u, and u equals g of x, so the inner function is g of x, then dy dx is derivative of y with respect to u, multiplied by the derivative of u with respect to x. So we're taking the derivative of h of u with respect to u, and then multiplying by the derivative of u with respect to x. So you can see here that if we let y equal sine u, and u equals x squared, then we get the derivative of sine of u is cos of u, multiplied by 2x, because the derivative of x squared again is 2x. And so that gives us cos x squared multiplied by 2x. In any case, the green line is our original function, f of x squared sine x, and the blue function is 2x cos x squared. So again, the blue line describes the gradient of the green line at every point. All right. Hopefully that's making some sense. If we look at some important functions for this course, the derivative of tan of kx. Okay, now remember that k represents a dilation by a factor of 1 on k from the y-axis. So if we let f of x equal tan kx, then f dash of x equals k sec squared kx. Okay, and just a small proof here. I encourage you to pause the video and apply the quotient rule, because we know that tan of kx, we know that tan is sine divided by cos. And so tan of kx equals sine of kx divided by cos of kx. And so the quotient rule, if we apply it, gives us this, right? And collecting some like terms, I should say rather, sort of multiplying the terms together. So you see here that we get cos of kx multiplied by cos of kx. So that becomes cos squared kx. Similarly over here, sine squared kx. Yeah, and then you can take k out as a factor out the front, and you'll notice you get this. And this is actually one. This is what's called the Pythagorean identity. And I probably should have put that in the prior knowledge, but we know that sine squared kx plus cos squared kx equals 1. And I encourage you to think about the unit circle for why that might be the case. Anyway, we're going to get k over cos squared kx, and we know that 1 over cos squared kx is sec squared kx. So you could express this as k over cos squared kx, or if we use our reciprocal trig functions, it's k equals sec squared kx. Okay, again, picked sort of diagrammatically, we got this situation going on. In green, we have f of x equals tan kx. At the moment, I think k is just 1, but we could change that if we wanted to. And in blue, we have f dash of x. That's the derivative of the green line. And we know, hopefully, from your trig in methods, or from before that even, that tan, so the green line has, and the blue line, in fact, has vertical asymptotes at odd multiples of pi on 2. So there's one here, there'd be another one here at 3 pi on 2, 5 pi on 2, and so on. I might just show you what the k does, so just give us a moment. Yeah, so this k value, if we change it, it's a dilation. So if it's at 2, it's a dilation of 1/2 from the y-axis. Okay, if it's negative, it's going to flip everything. So it's a reflection in the y-axis. Looks like it's a reflection in the x-axis, doesn't it? It's because tan of kx is an odd function. Have I got that right? Yeah, tan of kx is an odd function. So reflecting in the x-axis and reflecting in the y-axis has the same effect. I want to make sure that's right. Yeah, that's right. Tan of kx is odd. So that's why it looks like a reflection in x as well. It's actually a reflection technically in y if k is negative. If we wanted to reflect in the x-axis, we put the negative out the front. But yeah, so there you go. Interesting enough, I think. If it's 0.5, by the way, it's a dilation by 1 divided by 0.5, which is 2. So it's a dilation by a factor of 2 from the y-axis. I'm just pointing that out because I think transformations can be quite challenging in the course. All right. I should obviously say as well that there's asymptotes in the negative direction as well. Negative pi on 2, negative 3 pi on 2, and so on. Okay, the last function that's really important for spec maths to understand the derivative of is log e of mod x. Okay, and just to remind us what this mod means, remember it means that for x values, or think about it like this. So log e of mod x is 2 functions in one. It's log e of x when x is greater than 0, and it's log e of negative x when x is less than 0. And remember, log e of negative x would represent a reflection in the y-axis. So if we just look at the right-hand side here, this is log e of x, where x is greater than 0, because we have positive x values, and log e of negative x when x is less than 0. So it's a reflection across the y-axis. That's why it's been flipped across the y-axis. Okay, and obviously the domain, you can see, it doesn't, this asymptotes, it looks like they touch, but this asymptotes along the y-axis. So the domain is real numbers not including 0. And the derivative, well, we can sort of sketch it out. If I show you here, just to sort of reiterate this idea of differentiation, I've got some random point on the line f of x. If we're to take that point and graph the slope of this line at all those x values, you'll see that this blue point will trace out the slope of the pink line, and let's see what we get. All right, looking good. So the gradient, just recalling here, the gradient is negative, but it's very small. So that's why our y values are negative, but very small. And then they rapidly become still negative. The left-hand side always has a negative gradient, but they become larger really quickly. So we get something like that on the left-hand side. And then if we keep going on the right-hand side, we're going to get something like this. The gradient is now really positive. If it's down here, it's really positive when x values are small. And then as x values get larger, the gradient gets shallower. So it's less large and asymptotes along the x-axis, which means the y values are getting really, really small, but not getting to 0. And you may have seen this graph before, hopefully by this stage. This is tracing out the graph 1 on x. So that's an important that's an important function for this course. So important to know about, and you can hopefully see why that's the case. All right, good to be back. Hopefully you're finding that useful. If you have any questions, feel free to let me know. If you need any private tutoring, let me know as well. Good luck with all your exams, and give us a thumbs up if you found it useful. Good luck with everything you're doing. I'll talk to you soon.